When two resistors having resistance R1 and R2 are connected in parallel, the equivalent resistance of the combination is 5 ohms. Which one of the 5 statements shown here about the resistances is correct? So in this question, we have two resistors that are in parallel, connected to some power source. And all we know is that if we find the equivalent resistance of this circuit here, in other words, if we combine those resistances to give us, instead of R1 and R2, if we try and find an RT, we know that that RT is equal to 5. And we need to determine which one of these statements is true about the resistances R1 and R2. So to jump right to the answer before we do some work to kind of show that, that reasoning, the answer is going to be number 5. And number 5 says that both R1 and R2 are greater than 5 ohms. And the reason this is because the equivalent resistance of a parallel circuit, in other words, RT, will always be less than the smallest individual resistor in combination. So R1 and R2 are always going to be greater than RT. That's just a property of parallel circuits. So let me write that down first up here. So RT will always be less than the smallest resistor R in combination. So that means that R1 and R2, I wrote this as an R1 up here, R1 and R2 will always be greater than the resistors, the individual resistors in combination. So let's go about showing that. So if we think about our two resistors in parallel, we can use the 1 over RT equals 1 over R1 plus 1 over R2 to solve this. So 1 over 5, because that's our RT, equals 1 over R1 plus 1 over R2. And what we can do is multiply both sides, multiplying the numerator by R1, R2. And we're going to have a little bit of canceling. We're going to lose the R1s here and the R2s here. And then if we take this all and do some cross multiplication, so moving the 5 to the numerator on the right side, and then moving the R1 plus R2 to the denominator on the left side, we'll get this equation. 5 equals R1, R2 divided by R1 plus R2. And this describes the resistances in our parallel circuit. And we're going to use that equation to prove the other 4 statements as false. So let's look first at statement 1 that I have listed here. Both R1 and R2 are equal to 5. Well, let's see if that's true. Using the equation that I just put a box around, let's see if we can get the left-hand side equaling the right-hand side by assuming that R1 equals R2 equals 5. So we would have 5 equals 5 times 5 divided by 5 plus 5. So we would have 25 divided by 10, which would tell us that 5 is equal to 2.5. Well, that's not true. So statement 1 is false. Let's look at statement 2. Both R1 and R2 are less than 5. Okay, let's try, for example, setting them as the number 4. So we'll say R1 equals R2 equals 4, because that's less than 5. And then we'll test out our equation. So we're going to have 4 times 4 in the numerator, which is 16, and then 4 plus 4 in the denominator, which is 8. That gives us 5 equals 2, which is definitely not true. And if we try another example, say a smaller number, let's say R1 equals R2 equals 3. So we're making it even lesser than 5. Again, we can test it in our equation. 3 times 3 is 9, and then 3 plus 3 is 6, and that gives us 5 equals 1.5, which again is not true. And we can see that the number on the right-hand side of the equation is decreasing. So it's not getting closer to 5. So statement 2 is also false. Statement 3 is the sum of R1 and R2 is 5. This one's a little bit longer, but very interesting. So let's test that out. 5 is equal to R1 times R2 divided by R1 plus R2. But we're told that that is equal to 5. The sum of R1 and R2 is 5. I can multiply or cross-multiply the 5 in the denominator to the numerator on the left-hand side, giving me 25 equals R1, R2. And then I'm going to solve for R1, and I'll have 25 divided by R2. Now, there's two possible, assumptions you can make at this point. The first is that R2 is equal to 5. Well, if we do that, then we would have R1 equals 25 divided by 5, which means R1 is also equal to 5. But that's not possible since we tested that up here in number 1. R1 and R2 both being equal to 5. It didn't work out. So that is not possible. As for the other case, let's assume instead not that R2 is equal to 5, but that it's some other number. It doesn't matter, just not equal to 5. Let's assume that R2 is equal to 2. It could be greater, it could be smaller, it doesn't matter. The same thing will happen. We'll have R1 equals 25 divided by 2, which means that R1 is equal to 12.5. But the problem is we assumed that the sum of R1 and R2 right here is 5. But if we take the R1 and R2 that we just found, R1 plus R2, R2 is given here as 2, and then R1 we just found is 12.5. 2 plus 12.5 is 14.5. But we assumed that R1 and R2 summed is 5, not 14.5. That's a contradiction, right? So that is not possible either. This also explains away statement number 4, which says that one of the resistances is greater than 5. For example, this 14 or this 12.5 here that we found. And one of the resistances is less than 5, which is, say, this 2 that we found. We just showed that that is not possible. So we come to our final statement. Both R1 and R2 are greater than 5. And this is true based off of the statement that we made at the very start. But let's show it mathematically. So let's just pick a number that's greater than 5. Let's pick 6. We'll say that R1 and R2 are both equal to 6. If we go and do that, we'll get 5 equals 6 times 6, which is 36, divided by 6 plus 6, which is 12. That gives us 5 equals 3. Well, that's not true, but let's try a different number. In this case, you could test the number, say R1 equals R2 equals 7. You would have 49 divided by 14, and you would actually have a number that's higher than 3. So if you keep going, you're going to get numbers that are getting closer and closer to 5 until you get to R1 equals R2 equals 10. That's the magic number. So writing out our equation, we have 5 equals 10 times 10, which is 100, divided by 10 plus 10, which is 20. 20 goes into 100 5 times. And we find, finally, that 5 does equal 5.